Hello friends, welcome to the today's lecture. In today's lecture we will discuss the concept of calculus of variation. In fact, this is the first lecture of calculus of variation. So here in this lecture we try to discuss what is calculus of variation and what we try to do in this calculus of variation and how it is related to your usual classical analysis. So here to start with, let us consider the this definite integral, the Iy, and this is a definite integral from x1 to x2 f of x y dy by dx, and this integral is with respect to d of x. And we know that this is a well defined quantity provided that this integrand f is a given function of x, y and dy by dx, and here y is a given function of x, and this will give you a number provided this x1 and x2 are having some kind of definite numerical value. So we say that in calculus of variation the first problem is to find out, say, the values corresponding to different functions y, and we compare the values of these definite integral corresponding to the given function y. So we can say that the first problem of the calculus of variation involves comparison of the various values assumed by this integral denoted by 1 when different choices of y as a function of x substituted into the integrand of 1. It means that we have a value if y is replaced by some y1, and then if we replace this y by some other function, say y2, then we may have two different values of this integral. And in calculus of variation we try to compare these two values and try to find out a function for which the value of this integral is either maximum or say minimum. Or you can say that here we want to find out a particular function y, which is a function of x, that gives the value of this different integral as its minimum or maximum value. So it means that once a definite integral is defined in terms of say functions of this another function y of x, we try to find out, say, a function of y in a way such that this will achieve its maximum or minimum value, right. So in calculus of variation we will discuss these kind of problems in details. So so in calculus of variation we try to consider problems which can be transferred into this kind of definite integrals. So here there are certain problems, and some problems includes the problems of shortest distance between 2 points on a given surface. What it means that suppose we have a surface, it is like you have a surface here, and then you try to find out that there are 2 points A and B, and then we try to see that what is the shortest distance between these 2 points, provided that these 2 points lie on a given surface. So this is one of the problem discussed in calculus of variation, and we'll discuss this problem in detail as the problems known by geodesics. So such curves which gives the shortest distance between A and B are known as geodesics, that we'll discuss in due course of time. And the second problem, very important problem, is the quickest descent between 2 points. So it means that how we can say consider this problem, that suppose in a vertical plane we have 2 points A and B. Of course they are not on a same height, and then we try to find out the curve connecting these 2 points A and B in a way such that if we take any particle say which start from the point A and it falls under the influence of, say, gravity from A to B, then it will take least time from reaching A to B. So it means that the problem of quickest descent is the problem of finding the curves such that under which if we particle slides from A to B under the influence of gravity will take the least time. Okay, so that also we'll discuss in detail, and that is the problem known as Brachistov-Krohn problem. And this is the first problem which is supposed to be the beginning of calculus of variation. We'll discuss this problem also. And the one more important problem related to calculus of variation or discussed in calculus of variation is the surface of revolution of minimum area. It means that suppose we have a say one function, say a y, which is a given function of y of x, then we try to between say 2 points, say x1 and x2, and then what we try to do here, we simply revolve this curve around this x axis with the angle 2 pi, then it will generate a kind of here just like this. Okay, so here it is x2, and then we try to check the surface area of the revolving surface, and we try to find out the curve y of x such that the surface area of the figure so obtained has a least surface area, that we try to discuss in this. So here we try to see that we'll discuss these problem in detail, that all these problems can be reduced in finding the maxima minima of the definite integral posed like this one. So all these problems can be termed as, or can be written in terms of some kind of definite integral which depend on the say some function y, and we try to find out say minimum and maximum value of these definite integrals. And these details or this methodology is closely related to the problem of maximum and minima in the elementary differential calculus, or I can say that the techniques of solving the problems of minimizing or maximizing of different definite integral given in one and related definite integrals are closely connected with the problems of maxima and minima in the elementary differential calculus. We try to see how it is this. So now these definite integral are termed as a name which is known as functional. So what is functional? A functional is a mapping which assign a definite number to each functions belonging to the same class is called functional. So if you remember, we have written down our definite integral like this. It is from x1 to x2 f x y and y dash d of x. So it means that if you take a value y here, then the corresponding value is given by I of y is this. So it means that for any given function y, there is a value given by I of y. So basically it is a kind of a correspondence between a function to a value. So it means that it is some kind of a generalization of a usual function. So we can say that a functional is a kind of function. So it is a kind of function which say correspond between y to f of y to I of y. So here we can say that that a functional is a kind of function where the independent variable is itself a function or a given curve. So here functional can be generalized as a generalized version of a function. So it is also a functional, the only thing is that independent variable is already a function of some function of x. So functionals are often expressed as definite integrals involving functions and their derivatives. So in general you can define any correspondence between functions y to the value I of y, and so there are certain way you can define I of y as a this will go to say, you can simply say, you may define it like this also, y of x naught, where x naught is some point in domain of say y. So here also this also represent your functional, but here in calculus of variation we try to consider the functional which are termed as, or which can be written as these kind of forms. Okay. So here we will discuss that functionals are often expressed as definite integrals involving functions and their derivatives. So in general we try not to discuss these kind of functionals. Okay. So and the study of functional plays a very important role in many problems in analysis, mechanics, geometry, geometrical optics, theory of elasticity, quantum mechanics, etc. So that we see as an application of calculus of variation. We will consider certain problem of these fields as an application of calculus of variation, that will shortly will discuss. For the beginning we can say that the arc length L of a plane curve connecting two given points is also a functional. What is this? So initially if you remember, if we have a surface and we have a 2 points A and B and try to find out say minimum length between minimum length of this curve connecting these 2 points A and B. So let us say that this surface is a planar surface, or you can say that these 2 points lie on a say xy plane or yz plane or something like that, and we try to find out say minimum distance of the curve. So here what we have, let us say that we have a xy plane. So here we have xy plane, and then we have a point A and we have a point B. A is given as x1 y1. So here this is your x1 and the corresponding is your y1, and here we have say another point say x2 y2. So here we have x2 y2, and then we try to find the we can draw many curves connecting this A and B, and we try to find out that curve which minimizes the length of the curve connecting this A and B. So here I can say that if we look at the length of y, it is given by say x1 and x2, and if we take this as d of s, then we can simply write d of s. So it means that length of y you can define as the integral between x1 to x2 of this line patch line element. So here if we represent this y curve as y is function of y of x, then you can say that d of s is given by x1 to x2, and this is 1 plus dy by d of x whole square and d of x, where x is lying between x1 to x2. So we can say that the length of the curve connecting A and B is given by this functional, and this can be simplified into this x1 to x2 under root 1 plus dy by dx whole square d of x, and then this is one of the functional we are discussing. Now if we consider in case of planar region, if we consider these 2 points lying on a surface, then it means that in place of A and B lying in a plane, if we say that it is lying on some kind of say some kind of a surface, then not only we have to minimize the we have to consider the length of y, but also we have to put a restriction that these 2 points A and B lying on a given surface. So the length of a curve connecting 2 points is termed as a functional here. So here we can say that this Lyx is given in x1 to x2 under root 1 plus y dash square d of x. So here if you use one function, you will have a one value of this indefinite integral. If you use another function yx, then we have another value corresponding to that function, or you can say that given one curve there is a different length. If you use another curve, then we have a different length. So if we can use this, then this is y, this is y1. So we can say here we have a value, or you can say length of the curve connecting through this curve, and we have another length if we use this y1 as a curve. So we can say that this Ly is a function of your variable y, which is a function of x also. So we can say that this is a functional. Similarly, the area S of a surface bounded by a given curve is also a functional, and since this area is determined by the choice of the surface. So we have a, say, curve C. So let us say that we have a curve C. So this is, say, this is the curve. Now here this curve is bounded. So we have a surface. So we can say we have a surface like this, we may have a surface like this, and any you can consider like that. So we have a surface like this, and this is C is the curve which bound this surface in this area. So here we want to find out the surface area of these surfaces which are bounded by the curve C. Is that okay? And we can say that if we choose this surface, then surface area is different. If we choose this surface, then the surface area is different, and similarly whatever surface you choose, your surface area is quite different. So we can say that here your surface area S, which is given by, say, d of S over this region, we can call it, say, d dash. So we can find out the surface area based on this d of S, where d of S is the, say, surface patch on this surface d of S. So if I take say one surface, say z equal to z of xy, right, and then this can be written as double integral over d, and this is this surface area element can be written as 1 plus y dash, means dy by d of x whole square plus dz by d of x whole square and d of x, and here d is the projection of this on xy plane. So here d is denoted as the projection of your surface bounded by this C on the xy plane. So sorry, here it is dx dy. Okay. So here we can say that the area S of a surface bounded by a given curve C is also a functional, because if you use a different surface, your surface area is different, and since this area is determined by the choice of surface Z, which is given as Z of xy, so area S is given by this. So here your functional related to surface area is given by d, integral over d under root 1 plus z dash square plus z y square double z by double y square dx dy. Oh, so there is a small problem here. Here it is. Here it is. So there is a wrong thing. So here it is dz by dx whole square plus dz by dy whole square. Okay, I am just correcting it. So here we can say that the surface area corresponding to the surface zxy is given by this double integral d, and this surface element can be written as under root 1 plus double z by double x whole square plus double z by double y whole square dx dy, and here this d is the projection of the area bounded by the curve C on the xy plane. So this is also an example of a functional. Now we may also define a functional in the sense of center of mass. So if we represent that this function y equal to yx is made of some kind of material, then we try to find out the center of mass of this material. So this y of yx will give you some kind of a curve which is made by some material, and we try to find out, say, center of mass here. So we can we have already seen that this can be written as x bar equal to ratio of two functional a to b x under root 1 plus y dash square d of x divided by a to b under root 1 plus y dash square d of x. So this is the x component of the center of mass. Similarly, you can find out the y component of the center of mass. So in that case, your y bar is defined by, you simply replace by x by y. So this is also the functional. So it means that if you change the y of x, then your center of mass is going to change. So it means that if you change this curve y, it means if you are changing the shape of the shape of the material, shape of the say graph, then its center of mass will also change. So next thing is the problem of minimal surface of revolution. This we have discussed, that if we have a curve y equal to y of x and is rotated about the x axis through an angle 2 pi, then the resulting surface bounded by the plane x equal to a and x equal to b has this area. So this we can write it like this. This we have in fact drawn, but let me write it here. So here we have, this is x, this is y, and this is the graph y equal to y of x, and this is your a and this is b, and this is rotated through x axis of, say, okay, so it is this thing. So now we try to find out, say, surface area of this. So if you look at here, this we can patch it, this to entire shape can be truncated into these kind of patch, and we can call this as patch as, this is the surface patch like d of s, and we can say that y is the, say, radius of this circular patch, and you can say that the surface area is given by 2 pi y and d of s, right. Now here since I am discussing only line integral, so we are considering only, say, single. So we can write it here, 2 pi y d of s, d of x, d of x. So and this is, we are considering only between a to b, so we can write it a to b. So we can say that the surface area of this generated shape is given by a to b, 2 pi y ds by dx d of x. So you can find out, say, ds of dx as, here you can write d of ds by dx is equal to under root 1 plus y dash square. So here y dash represent dy by d of x. So here you can say that the resulting surface bounded by the plane x equal to a and x equal to b has this area, s equal to 2 pi a to b y under root 1 plus y dash square d of x. And we so this is also one example of functional. And if you look at, in general, we can define, say, general example of functional as this, with the help of a continuous function f, which is continuous in terms of its arguments. So it means that function f is continuous with respect to x, y and z. Then you can define functional defined as this, j of y is equal to a to b f of x, y dash x, d of x. So here if you look at, then by taking a particular values of this f, you can say that this first problem, that is the length of the plane curve and the surface area and the area surface area is also can be considered as a particular case of this. And here we may consider one more property, that is, these kind of functional is having a localization property. What is localization property? That here we can truncate the region of y of x. For example, this particular problem, here we can consider this y of x, and then we can truncate the region between a to b into smaller parts, and for each smaller part, for example, we have this a to, say, x1 and then x1 to x2 and so on. So here we can divide this entire range a to b into several sub patches, and we can find out, say, corresponding functional, and find out the value of each functional. So it means that you can say that for example here we have j of y is equal to a to b and f of x y y dash d of x. So here in for this particular problem your f x y y dash is given by 2 pi y dsx ds by dx. Now I am saying that if we want to write it, say j1 y, what is j1 y? Here you write it a to x1 and f of x y y dash d of x. So you can say that ji is nothing but this sorry. So j1 is between a to x1. Similarly you can define j to y is equal to your x1 to x2 f of x y y dash d of x. So similarly you can find out patches, find out say functional defined in these sub patches, and then if you sum all these values then you will get the values defined by this original linear functional defined by jy equal to a to b f x y y dash d of x. So we can say that this has a localization property, but if we consider this part the functional defined here, this is not having this property. Here we cannot do this thing. So we call these kind of functional as non-local functionals, and in calculus of variation we generally deal with the functional with the localization property. So in calculus of variation we generally deal with local functional, not this non-local functional. There are certain functions available, some methods available to deal these kind of problems. There, for more general example we can consider a continuous function fx y z, which is a continuous function with respect to its argument. Then a function may be defined as j of y equal to a to b f of x y of x y dash x d of x. And here by taking particular examples of f, you can consider that the problem, this problem which is the arc length of a plane curve and the surface area of a surface bounded by say a given curve C, and the problem of minimal surface of revolution given by this equation number 2 is a particular case of this, right. So here summarizing all this, we can say that the calculus of variation is a branch of calculus of functionals in which we find the maxima and minima of the functionals. And we can say that there's the calculus of variation. In this branch we discuss the methods that permits finding maximal and minimal values of functions, and the problems in which we investigate a functional for a maximum or a minimum are called variational problems. In fact there are certain principal rules in mechanics and physics that can be related to functional, that can be related as the maximizing or minimizing some kind of functional in that process, and they can that rules can be converted as a maximizing and minimizing of that functional. So that kind of problems are also known as, that kind of rules are also known as variational principle. So that also we will discuss in calculus of variation. So for today's class we'll bind up things here. In next class we'll discuss the concepts and basic definitions of calculus of variation. Thank you for listening us. Thank you.